joined.
So at least for the admin, it shows up in the left corner. Right now it's 0, I'm guessing.
Can you make me admin?
You'll have to log in. Let me see if I can make you an admin right now. Oh no, it says I can kick you from the studio, but I can't make you an admin.
Please don't kick me.
We already have people joining. I asked Thomas how chai is he. He says I'm pretty chai right now.
Oh, hold on. How do I'm not able to comment. Uh,
Hey, simply Sumant.
Sanyam, you've got to fix my settings. You've got me on the show, but you're not letting me comment.
It's your show as well. I need to. We'll figure it out afterwards. No worries.
All right, I'll let you do that stuff. So anyway, all right. Well, Sanyam kind of convinced me to have enough chai again today, so I'm still up and still going at 8 p.m. And I
Yeah,
think today,
if you were wondering what we do on Friday evenings, I mean, I'm sure you weren't, but now you know.
yeah, especially COVID Friday evenings.
Yeah.
So I guess first, everybody, I'm really curious to see like, I think this is mostly an informal one. This is not something that's a formal setting, or this is basically meant to be more interactive. And the idea is that we learn publicly. So that's the idea. Like basically, the idea is it's not like a well rehearsed sort of a thing. It's not like, oh, we're very well practiced, or like we've come with 2 weeks of preparation and then we're doing this live stream. It's mostly you'll see through the faults, but we learn through the faults. So basically we make mistakes and we learn in public. Like that's the main idea of this show, or basically doing these live streams is we show the process of how we actually go about these things, or what really it takes. And then as part of that, we're also gaining like learning how to learn things, learning how to learn new things. So at the same time, it's like doing it just publicly, like having you guys as the community, and that's the main goal over here. um and having said that, then what we're doing today is looking at the Google landmark 2020 solution, so recognition solution. And
Not the
I
retrieval one. That was my fault. I'm sorry.
That's okay. And something I realized is that back in 2020, I wrote a blog post about gem pooling, and it's just I've completely forgotten about gem pooling, but I've written about it somewhere. And then I'm just gonna go back to that and show you guys everything. And when I was participating in 2020 landmark recognition, obviously I didn't get a medal because I was like, I used to give up on things at the time, but now things have changed. Sorry, there was a bit of background.
Is it
Oh, that's
fine?
my yeah, it should be fine. Sorry, it was just my Bluetooth headphones.
I didn't catch
Anyway,
anything.
that's good. So then I guess then the idea is now we want to participate in Landmark 2021, and for that we want to learn about what it took to win Landmark 2020. So that's the first place that we're going to start. So having said that, let me then just quickly share my screen, and we get started with the 2020 solution.
Absolutely. I mean, we won't mind streaming as we learn about the 2021 either, but that's against the rules, so we won't be doing that. And
Yeah, we could have done live. Like for us, the uh, idea is not like we're not this secretive people who uh, learn something and then not share it with anyone because we feel like it's a secret, so we don't want to share it with anybody. We're these people who make faults in public, and then we share it with everybody even still. So that's the main idea. And oh, hey Megraj, that's great to see. Welcome. And then that's the idea. So I think enough talking. Let's get started.
sure.
All right. Um, so this is 2021. This is not and best fitting is at 20 in the 2021 competition, and he's doing the best fitting, basically
Do you
doing his
know
thing.
about best fitting, Aman?
I know of him.
Mm-hmm.
As in when you say about, like, what do you mean?
So he started a while ago on Kaggle, and he's supposedly, if I remember correctly, the leader of a company. I think CEO, and he would just straight up land in gold zones in every single competition that he would enter. So he's this Kaggle legend that if you see him on a leaderboard, he'll definitely be in the top three. He's recognized as that person.
Certainly feels that way, and I knew that much. I knew that he's someone who's to be well respected.
Yeah,
um, I'm just kidding. So yeah, I think that's just it's like when you see people like these, it's just inspiring, and you take inspiration from them, and you go, oh, is there something they do different? But it's actually persistence, I guess. He's been doing things long enough, so I see competitions from like 5 years ago, and after 5 years, then he's in the gold range. So I think it's more persistence than some magic.
yeah.
But that's just my opinion. So then that's really good. I'm really quite happy. So let's get started with Google Landmark Recognition 2020. So as it says, I'm just gonna do a quick introduction. I hope everybody knows what the idea is. But sorry, give me one sec. I just need to stop sharing and then
Sure.
duplicate my displays so I can use OneNote. I'm just fixing that.
Because reading code is difficult, can you make more content like this? That's the plan, Nugin. I hope I'm saying your name correctly. We just Aman and I would be doing this in our Zoom calls. We're just doing it. We're just broadcasting it so that you all can learn along with us. Which means we'll be embarrassing ourselves a lot. But yeah, that's the plan, to learn together with all of you.
Absolutely. And then we can do lots of live streams on code. What kind of code streams are you after?
I guess they want to learn more about top solutions. So I feel for Kaggle there are these levels of depth. You can know about a solution, then if you've really taken part, you can understand how they did it. And if you can find their code or just replicate that, now you have this complete picture. So I
Yeah.
don't know which level are we aiming for, but certainly at least in the second or third.
Yeah, I think in my head, I'm aiming for understanding a solution, then reading through the solution in terms of code, and then picking up those ideas and trying to re-implement it in maybe 2021 solution. So that's the process that we're going to follow. And I think every week or every second day that we come back and we do this live stream, we're going to try and make more progress. So if today we look at gem pooling, then we're going to try, okay, what's arc phase next? Or like there's just we learn more and more about metric learning as we go, and then we just go deeper and deeper. So I'm definitely aiming for something that learn the solution. And for me, a solution isn't complete, or a paper reading isn't complete, or a blog isn't complete if it doesn't contain code. So that's just been my ideology for a long time, and I kind of completely abide by it. So that's going to be the same approach for Kaggle as well. So just going to try and make an introduction. So I just need to duplicate my displays again because I think that didn't work the first time.
No problem. Sai, we do plan to cover different frameworks as well, but as we implement these solutions, we're fans of Tim library. Aman is a contributor. I'm more of a fan. He's more of a contributor. But yeah, we will be covering those whenever it makes sense. The idea is to be in a top-down fashion, just like FastAI, where we're actually implementing things. So we're focused in that direction.
Yeah, and for Landmark, for example, they're using PyTorch Lightning instead. So that's a new framework right there. So we and for Fastbook, we are covering Fastbook reading group at Weights and Biases, which is again a different reading group that we're doing. And so that becomes FastAI. Then for PyTorch, we have other live streams that we'll be doing at Weights and Biases, and then this is again something that we're doing using PyTorch Lightning. So there's a good mix of different frameworks that we do try and cover and learn as ourselves as well. So with that, let's just go through this and let's just have a read. So this is the introduction. I think it's really good to know what exactly you're meant to do in a competition. So let's just go through this. Welcome to the. So this is 2020.
I
So this is
don't see
the.
your screen yet. If you share
Oh,
that,
I'm so
Aman.
sorry.
No
Uh,
problem.
can you see it now?
I'm just adding it.
Oh,
Yes.
1 second. Okay. Same if there's any, because I can't see the screen anymore, and you pretty much see what I see on my
Sure thing.
screen, which is just this in front of me. If there's anything or any question that comes up, feel free to bug me, because if I go to StreamYard and if I start reading, then that this
Yep.
is what happens to the stream.
The Inception
So
scene. Yeah.
yeah, so it's just better that I don't do that. And let's get started then. Okay, so then with recognition, because the recognition competition has been running since 2018. So there was 2018, 2019, 2020, and then 2021. So they've been doing Google has been doing the same thing for 4 years in a row now, and 2021 is the fourth such competition. So 2020 was the third landmark recognition competition. And then the question is, have you ever gone through vacation photos and asked yourself, oh, like, what was that place, or like, what was that temple, or what was this landmark that we saw? Um, and then you want to like recognize that landmark. And what you could do is now use this competition or use deep learning and upload that image to this basically API or the models that Google has trained, and then that way they can recognize the landmark straight away. But the challenge with doing this is that there's over 200,000 labels, and the images are over 5 million images. So this particularly this landmark recognition competition, when it first started with the whole data set, had over 5 million images, if I remember correctly, and it had over 200,000 labels. So let's just have a look at the 2018 actually competition, so I can confirm like how much data they had. So again, I'm just learning as we go. I'm just going to go to the data and just see and read like how many labels they had. So let's see, is there any information about the
I
data set?
I
Let's
think for
have a
this
look.
one you had to download it from somewhere if I remember correctly, and that's why I bailed on this
Yeah.
competition because my internet would crap out.
And they're saying if you make use of this data set in your research, please consider citing this research paper. So let's go to that. Oh, sorry, not this, not the YouTube video, but let me just copy paste this and you go here. So let's just have a look at what this research paper is, or what it is about.
I
So
think
what
it
they're
was a
saying is,
2017 one. It's just the
yeah,
same
yeah,
one.
I'm just very curious. We
Okay.
propose an attentive. Oh, this is Delph. Okay, I've seen this before. Um, Cool. Let's not go into the details of that. I'm going purposefully skipping over that for now. What is this one? To avoid bias, no computer vision algorithms were used for ground truth generation. Okay. And then does this say anything about the amount of images that they had? The test images are here, nothing over there. Evaluation, nothing over there. In terms of data description, oh, there it is. Since this challenge is finalized, the data were transferred to this particular page, Google Landmark Dataset, and then let's read about this dataset. So it's saying data was originally described in one, which is, where is one? So it's this one. Okay, so that was the local. Sorry, so Delph is the place where this landmark. Okay, there we go. To evaluate the proposed descriptor, as in they introduced a new technique which was called Delph, Deep Local Feature, and they introduced a new data set back in 2016. That's when this first
Hmm.
paper came around. So this is back in 2016 when Google did this, and this referred to as Google Landmarks dataset. It involves challenges in both dataset and query, such as background clutter, partial occlusion, multiple landmarks, and that. Okay, interesting. And then they provide the code, and dataset can be at this particular URL. So let's go to that URL and let's just see where is the dataset. So as you guys can see, I don't really have like, ideally I would like to have all these tabs open, but because I don't know, there we go. So the Google Landmarks versions are two. There's initial version, which can be found here, and then the second version that has been released as part of the two Kaggle challenges, landmark
Hmm.
recognition and landmark retrieval. That's what we want, and it can be downloaded from CVDF. And then there's also a CVPR paper. So they kind of started, I guess the background is then they kind of started in 2016.
17, 16? Yeah.
2016 December, because that's when this paper came
Hmm.
about. And then they've been refining the data set every year, and they've written research papers about it. So as it says, we now have also made available Google Landmark Boxes dataset that contains 86,000 founding boxes. Does it say how many million images it contains? I just want to have a look.
Um,
So images,
Maybe on the
images,
GitHub page.
maybe the training images are associated with landmark labels. So as it says, the training images, so each training image basically has a landmark in it, and then I guess we spent enough time on trying to find and learn more about this data set, but because that's not what we're here for today, so I'm just going to, that's it. I'm just going to time box myself and just introduce about this competition, about what I know. So then the first version of this competition, or the Google Landmark dataset, had over 5 million images, and it had over 200,000 labels, as I understand. So what that means is that it's not like your multi-label classification, right? Generally you'd have pets classification. So you classify, you have an image of a pet, and then you classify that to a dog or a cat, or like a specific breed of a dog or a specific breed of a cat, which is like, I think it's 39 categories if I remember correctly, but I could be wrong. But it's like a really small number. And then that's what we used to. That's much easier to train. It's much easier to do in deep learning. For example, the cassava competition had 5 categories, and then all those things. So that's much easier task to do. But when you're presented with 200,000 labels, then the one thing I realized about this competition is it's actually much more tough. A, the data set size makes it really tough, and B,
Yeah.
the amount of labels makes it really tough. So that's the very first version. And then in 2020, they had a version 2 of this Google Landmark dataset, as we read about it. And in that, what they did, you had about 1.5 million images instead of 5 million. So that was a subset of so that was a subset of 5 million. So you had like 5 million images to start with, which is called
Do you remember
V1.
how many images are there in ImageNet, Aman?
It's about 1.4 million. So then you
Hmm.
take a subset of this, which is your subset, which becomes your V2, and this had about 1.5 million images. Now, don't take these numbers as ground truth. It could be like 1.4 million or something. I'm just providing rough estimates that I remember from the top of my head by participating in this competition last year. And then the labels, if I remember, were about 81,000. I think some number like 81,131. Anyway, so
Mm-hmm.
instead of like having 200,000 labels for each image, you have like, I mean, you have 200,000 labels to choose from. You have 81,000 131. That's the amount of labels that you have. Okay.
Hmm.
So then that's version 2 of this, which is introduced in this particular competition. And then what you have to do is that for each image, you you kind of have to pick like what landmark it is from, and then you can see why this task is particularly difficult, because there's images from all over the world. So somebody could be taking a selfie, somebody could be like, it could be a different angle. For example, if it's the Eiffel Tower, if it's from the front, it might look different, but if it's from like top down, for the deep learning model, it's like there's all these different angles that you have of like the same monuments. If it's the Taj Mahal, it's like a different angle. And then what that does is it just makes this task really, really difficult. And then for some particular landmarks, you had like over 2,000 images. I can't remember the exact number, but there's like, for some landmarks, you have a lot of images. And then for the other landmarks, you have like 5 images. So then there's this really high unbalanced data set, imbalance in the data set. And you just have to work through all of these challenges. And uh, and then the approach that you might, or like the first approach that comes to mind, at least that's what came to my mind when I was participating in 2020, but thank God I've learned from it, learned from my mistakes. And so the first approach that came to my mind is like, you have these 5 million images. All right, I'm going to have my deep learning model, and I'm just going to do cross entropy loss, and I'm going to classify this into 200,000 200,000 classes. So it's like multi-label classification. So basically anything that you would do for the pets data set, I'm trying to do for these 5 million images.
It's
And
funny. This was my first thought right now, so I
right,
shouldn't have
okay.
said that out loud. But okay.
No, it's not funny at all. It's the first thought that you get anyway, right?
Yeah. Yeah.
Because you think, okay, this might work, but it doesn't. I don't know the exact specifics. as to why it doesn't work. I think it's got to do something with the unbalance. It's got to do something with, like, you have 200,000 or 5 million images and then 200,000 labels. So there's the model, while it learns to differentiate, it doesn't work as good as the popular approaches out there. So when I was first reading about this, like in back in 2020, which is about a year and a half ago, when I was reading about this, I saw and learned about this thing called gem pooling. So I knew of two poolings, which is average pooling, and I knew about max pooling. So those are the two pooling techniques that I knew of, but I hadn't heard of gem pooling until I've started participating in this competition. So when I learned about gem pooling, I saw, and the second thing I learned about was arc phase. So there's this thing called arc phase margin loss. Now, uh, don't ask me what they are because we learn together. And I've written a blog post on gem pooling, but I don't remember what it is. So we will go through this together. But I think if I remember correctly, you just update this pipeline and you have your image. So you have like these 5 million images. Then you pass it through a backbone. Okay. So this backbone could be trained on ImageNet. So when I say backbone, this is either your ResNet 50, it is either your EfficientNet, um, just any standard backbone. So you pick a backbone from TIM, which is my favorite library, one of the favorite libraries for PyTorch for doing this kind of stuff, and you take your pick of what backbone you want, especially if you want to do feature extraction. Then you have something called gem pooling. So instead of like having the pooling layer, because this backbone, so this deep learning model has many layers, right? So it has like so many layers. You cut it off at the point where there's the pooling. So you cut off that backbone. So now you have, instead what you have is called a feature extractor, right? uh, so what you can do now is, I'm just providing some background before going into the competition. Let me
Sure.
know if this is unhelpful and I'll stop. But if there's Sanyam, if you read comments and people are like,
Yep,
oh,
I'm.
why is he wasting my time? Then let me know and we'll stop. But basically, the idea is like you have an image and then you have a backbone, and this backbone has a pooling layer in the end. So what typically happens is, like, as this goes down, so you have an image of like 3 by 512 by 512. As it goes down and down into the network, by the end you get, so that as it goes down and down into the network, by the end you get something like, maybe you have 512 channels, but your feature size or spatial size is now 16 by 16. So this is like big, but has 3 channels. By the time you're at the end of the model, you have something like 512 channels. So this is 512, but the image size becomes 16 by 16. So you
The
really
depth is
make it
more, but
smaller.
the size is really small.
Absolutely. And then the next thing that you do is you pass this through a pooling layer. And then what that pooling layer will do is it will take this 16 by 16 plane. So see how these are all planes, right? It's a 16 by 16. These are all 2D planes,
Yeah.
right? You have 512 of these 2D planes. So what you take is, like, you could take the 16 by 16 and you could average it, right? So you take the average and you do this for all 512 of them. So you get, in the end, you get a 512 vector, which is a representation of this image. And then this vector can be passed through a nn.linear, or basically a linear layer. So you have 512 here. And then the next, you have however many classes you have. So n class, right? So then you pass this through your linear layer. And then towards the end, you get, if it's pets, you get like 37 outputs. So now what you've done is you've built something that can take an image as an input, and it's giving me out 37 outputs. And you could pass this through a softmax. So then those 37 outputs represent probabilities of those 37
Probabilities.
classes. Does that make
Right.
sense? So you have
It
like
does.
37, you have like 37 class probabilities in a way. Like, that's how you can.
So,
Um,
Aman, going back, when you're saying you'd replace the pooling layer with gem pooling, are you just replacing, let's say, max pool layers with gem pool, or how does that work?
Absolutely. So I guess what you could do, because this is backbone plus pooling, right? What you could do is you don't do the pooling. Oh, actually, let me just use a different color. What you could do is where's my red? Here it is. You don't do the pooling. You just take the backbone. So what is that going to do? You get a feature like this. You get, just keep this thing, right? 16 by 16, but 512 of it. So you have
Yep.
like a smaller feature map, but it becomes a representation of my image. Now, you pass that through gem pooling. I've forgotten what exactly it is. So it's again, it's some kind of pooling, but you still have this as your output. And then I think you pass that through gem pooling. We'll go through gem pooling together because I can't even remember the details of what exactly it does or how is it different. And then you pass that through gem pooling. Then you have a head or a neck, as you may call it. This neck is just like a linear layer or a linear ReLU linear. Okay. So this is the neck as I'm trying to type. Sorry, right. So it's like linear plus ReLU plus
Mm-hmm.
linear. And then in the end, instead of using cross entropy loss, you use something called arc phase loss.
Got it.
And then what this can do, like the way, like this is how you change the, this is how exactly you change the whole pipeline by doing two things. First is you introduce this gem pooling, and the second is you have this arc phase loss. So this is exactly how an image, now you can, like by following this second pipeline, which is this whole thing like this, uh, now you have something that can do image recognition for 200,000 labels.
Understood.
That's
That makes
my
sense.
understanding of it. um, so now if we have to go forward, let's learn about gem pooling or arc phase loss. But I guess now this provides enough context that we are ready to go through the first place billing solution.
Sounds good.
So in this
Thomas,
competition, yeah,
I was just reading the chat. Thomas is saying VGG for the win. Yeah, absolutely. We might also might as well throw in AlexNet for therein. Scott is saying maybe it's because there's a very long tail of rare classes. He's referring to the baseline not being well. I think that could be the case. Again, I'm not too sure. I didn't take part in this competition, so Aman, do you have
yeah,
any
me
thoughts?
neither. What's Scott saying? Sorry, is that Scott from work?
Yes. Hey Scott.
Oh, hey Scott.
Uh, so he's referring to the baseline not working well. When you were saying you would just throw in all of the examples, he's saying maybe it's because there's a very long tail of real classes.
Yeah, absolutely. As I said, I'm not exactly sure on why that didn't work, but pretty much the model doesn't do a good job, and it could be the unbalance. So definitely, I think that's a good point that you make there, Scott.
Mhm.
Anything else, Sanyam?
Um, Adriana is asking where did the 200k classes come in? So they
Or-
are part of the dataset labels.
Yeah, that's the Google Landmark version 1, as I
Uh,
remember.
Sumant is asking is ArcFace built into PyTorch or other libraries? Sumant will just be looking at this
Yes,
after this.
the answer is yes. I mean, it's not PyTorch native. Like you don't find that in the PyTorch library, but somebody would have a good implementation of ArcFace. Uh, so let me see actually if there's a ArcFace loss PyTorch.
How to handle huge data on Colab? Ask Professor
Uh,
Zachary Mueller. He's an expert and advocate of Google Colab much more than I am. But you could create subsets. Many people just for Kaggle competition, since it's incentivized. By that I mean when you upload data sets, you get medals. They upload subsets of data. You could just upload those and build a baseline on there. And then when you have the baseline and you're happy with it, you could just spin up an instance and train on that.
Absolutely. So then let's have a look at this arc phase loss. I'm really curious. But actually, before we look at the arc phase loss, I think because we're following the top-down approach, let's have a read of the first place solution, and then we take our pick of the things we don't understand, and then we go and understand those things. So I think that would be a good approach to follow, because that's one thing I followed. And then we can just start that top-down branch, and then we can see, oh, okay, we don't understand arc phase, we don't understand gem pooling, or there's if there's other things that we don't understand, then we just keep going like that. And then then what we could do, continuing forward, is like we could try and implement this in code, have a read through the code, and all that stuff. Now, because it's a longer thing, it's going to be done over the few days or weeks, depending on time availability. But that's just the process that we're going to
Yeah.
follow for Landmark 2020.
Debarshi has mentioned PyTorch metric library. Metric learning library has
Oh, is
arcs.
okay. I didn't know there's a PyTorch metric library. Thanks very much for
I didn't
pointing that
as
out.
well.
Let's have a look.
This is so incredible. We're just learning, and it's crazy to see people are also chatting with us. It's just mind blowing
Yeah,
at the same time.
I think it's more like a group study. I
Yeah,
don't know what to call it.
basically.
uh, So again, what is metric learning? I My understanding is limited, but I think when you have problems like this where you're trying to do face recognition, or like, so imagine when you're trying to do face recognition, imagine like you have some, because we keep reading in the news, oh, the police is using face recognition or things like that, and then, but how is that even happening? Like you have billions of people, and then you have uh, if you're looking at a specific country, then it could be anywhere. The population could be anywhere between 1 million to 1 billion people, and then these face recognition models are again faced by that same challenge of like having a huge number of labels. So I think when you have faced with this kind of a problem, it's called metric learning. That's my understanding. Like metric learning is suitable for those kind of problems, but let's see what metric learning is. Oh, there's a good scikit-learn
Awesome.
um, user guide. So scikit-learn is well trusted. So I clicked on it. Between towards data science and scikit-learn docs, I would always go scikit-learn docs. Not to say towards data science is any bad, but just a matter of preference.
Yeah, yeah.
Many approaches in machine learning require measure of distance between data points. Okay. Traditionally, practitioners would choose a standard distance metrics using prior knowledge of the domain. However, it is often difficult to design metrics that are well suited. Distance metric learning aims at automatically constructing task-specific distance metrics from supervised data in a machine learning manner. The learn distance can be used to. Okay, I remember now.
Hmm.
Um, Metric learning is basically just this idea of trying to find whether images are similar or dissimilar. So in a way, you're trying to find the distance metric. Like what you want to do is, if you're using cosine as a metric, cosine similarity, or like Euclidean distance, then this is distance metric, I guess. So metric learning is just basically this idea of like you're trying to learn the distance metric. If like two images, how close they are to each other, or how further away they are from each other. And if you think of it, for faces and landmarks, this is a good approach because all we want to know is like how similar images are. So um, if we have say if we have so if there's one sorry that's the 1 second, let me fix that. If there's 1K images that you want to classify, then you also have a training set of 5 million images, right? For
Hmm.
each of the training set you have labels. So this all of this has labels with it, right? And all of this has no labels, correct? So what
Yeah.
you could do is, if you take an image over here and you find, using a distance metric, you
Makes
find that
sense.
this image 1 is similar to this image 2, like it's the closest to this image 2, then you can take the label for this image 2 and assign it back to image 1. So in a way, you've done classification by using this metric learning approach. That's my
Got it.
understanding of it.
I mean, I'm not too clear on how does this fit into the, like, intuitively, how does this fit into the picture of the model backbone we had discussed? So, how is this helpful there? I'm not too clear
In
on that.
this,
Yeah. So, if we put
okay,
on arc loss in there,
yeah,
why is that useful?
that's a good point. So basically, somewhere in there, you basically extract an embedding from the images. So I think that will become more clear as we go through the first place solution. But
Okay.
what you're trying to do is, now, instead of like having your label as the final thing that you get as the output, instead what you have is you have like an embedding that's a representation of the image. So what you could do is, for each of these 1000 images, right? you could represent them as a 512 vector. So you have
Hmm.
a massive matrix of 1K by 512, because each image, remember, is now represented by a 512 vector. And you could do the same thing for 5 million images. So now 5 million images are all represented by a 512 long vector. And now you can find similarity between the two. So you find like, okay, is this image similar to this image or not? But that's just like, that's we'll this thing will become clearer as we go.
Okay.
So we were
No,
looking
that
at
was helpful.
PyTorch metric. Great, awesome. So we were looking at PyTorch metric learning, and okay, there's this wonderful library, which is the easiest way they claim to use deep learning in your application, modular, flexible, and extensible, and it's written in PyTorch. Cool. I will bookmark this and I will add it to my reading list. Thanks. Who pointed that out, Sam?
I think it was Deboshi. Thanks, Deboshi.
Excellent. Thanks for doing that. Um, Cool. So now let's get through the first place solution, because that's what we want to cover today, and I'm conscious of time as well. So in the first place solution, let's have a read. I'm reading this the second time. I'll be honest, I only read this the first time before, 10 minutes before joining the stream. So if I make mistakes, please go easy on me. So thanks to Google and Kaggle for hosting this yearly competition. It was a lot of fun exploring and learning all about global local descriptors and algorithms to match similar images. So they're using, see that's a good
Hmm.
thing. They matching similar images. So that's how you do classification on 200,000 labels. You match the image to something that's similar in the training set, and then you use that match, or like you use the label from the match, which becomes your prediction. Does that make
Right.
sense?
So it's helpful because it performs. I'm guessing better than classification. Just like straightforward classification. Is that how you feel?
Yeah, I feel that way, because I think for that many that large a number of that large number of labels, and especially when you have an unbalanced data set, it might be easier to just get a representation of the image, and then instead of like having a linear layer in the end that does 512 by 200,000, because remember the model also has to learn those weights of like 512 to 200, because remember in the end we had if you're doing any standard classification, you have like an nn.linear layer in the end, like this one. So you have a nn.linear layer in the end, which goes from 512, or like the output of the model vector, to number of classes. I think in this case it would be from 512 to 200,000, which is a massive, massive matrix, or like a
Makes
massive,
sense.
massive weights.
Yeah.
So even to learn those weights would be difficult, right? So it's much easier that you just get this 512 vector and you keep it like this, and then you just match it to the
Hmm.
massive data set. That's my
That makes
understanding.
sense.
Great. Cool. So then let's go about the brief summary. So our solution is an ensemble of 7 global descriptor only models trained with arc-face loss. Okay, so that's the first thing. Sayam, take note. We need to cover arc-face loss.
Sure thing. Yeah, I'm
Um,
taking notes on the side.
Excellent. So then 7 global descriptors. Okay. So some jargon is like, what's a global descriptor? What's a local descriptor? When I was first reading about this competition, actually, it might be helpful if I go to the blog, because I think I have images over there. So there's the gem pooling. Um, Query images. How does it work? Unsupervised, non-matching. This is another paper. Image pooling normalization descriptor, VGG, gem pooling, PyTorch. Okay, I don't have it. Sorry. I thought I thought I do. Never mind.
So much for suspense.
I know. Then again, it's just a simple thing, right? For an image, if this is my image, and then you have a descriptor for a part of the image, that's a local descriptor. Like if you represent a part of the image as a 512 long vector, then that becomes your local descriptor. But rather, if you represent the whole 512 long image and that represent as a 512, then that's a global descriptor. So basically it's just the context. If you have the whole image, it's global. If you have some part of the image, it's like local. So that's the idea. So they just
I
used.
I was just
Yeah.
going to say I remember reading about local and global descriptors in CV2 library. So this was pre-efficient net era, and just implementing them and like seeing them on examples was just so incredible. And that's how, like, if anyone wants to check this out, you can just run the examples in CV2, and that'll make much more sense than at least the deep learning part of things, and then you can understand this better.
Yeah. Thanks, Ayam. So then, okay, so they use 7 global descriptor only models. So they didn't use local descriptors. So everything you have is a global descriptor. Uh, just let me know if there's any background noise coming from my side, okay?
I don't hear anything.
Okay, that's good. Cool. So then the next thing is we classify landmarks by KNN on an extended version of the trained dataset and efficiently re-rank predictions and filter noise by using cosine similarity to non-landmark
Hmm.
images. We did not use any local descriptors. We did not use any local descriptors. Okay. That's just the brief version of it. That is fine. The main things that we need to take away from this brief solution in my head is that they're using KNN, which is just similarity. So you have your test set. You're trying to find similar images in the training set, and then based on that, you take your pick of the label, whatever the training label is. So they're using this exact approach that I've just explained, and based on that, you can classify landmarks. All right. Detailed summary. Below, we give a detailed description of our solution, of which architecture is only a small part. That's a good point. Generally, architecture is given a lot more weight than it should. So architecture is only a small part of the main solution. And then the next thing
Hmm.
is video content of us presenting the solution is available under NVIDIA Grandmaster. Oh, what do I see? This chat time data science. I didn't
Have you
know.
heard of this? It's a really
Uh,
good podcast, I've heard.
is it? Oh, there
Yeah,
it is. Oh, I know of this. Oh, all right. Okay. I swear I didn't know.
that's all right. It's it's pretty advanced, you know. It's not everyone's cup of chai. I'm just kidding. They were really kind to do. I think Philip's this was Philip's third interview on the show.
Yeah.
So they
I
really
was just
kind to me.
watching the NVIDIA Grandmaster one before this because I find it out. But this is also really nice. There's like these two video descriptions where they're explaining the video. They're explaining this. So let's go down to the pipeline. So they had a nice pipeline set up. So they said we wanted to use this competition as a chance to improve our pipeline and coding skills. While in past competitions, we mainly used Jupyter notebooks locally. Uh, they've basically used Jupyter notebooks. Okay, we switched to a collaborative approach of using scripts with GitHub versioning for this one. So for are there people who don't know what GitHub is, or like are there people who don't know or haven't used Jupyter notebooks or GitHub in the past? Saying in case you see a comment and somebody says yes, let me know.
Sure thing.
Um, so that's fine. So I'm just going to skip over this for now. So they kind of had all of these different pipelines. I'm just going to skip over this. So in practice, they downloaded the pre-processed data from Google Storage, trained our model and stuff. So let's just get down to the architecture. We'll go back to the pipeline when we're looking at the code. So let's have a look at the architecture. All right. So this is the architecture as I remember it. That is correct. So you have an image. You normalize your image. You pass it through a backbone, you do gem pooling, whatever that is. Sanyam, that's the second thing. Could you please take note that there's two things we want to
Absolutely.
learn, gem pooling and arc margin. So you have gem pooling, then you have neck, as I said, it is linear ReLU. So instead of ReLU, it's PReLU. So PReLU is, I think, just another kind of non-linearity. So that's fine. It's just an activation function that generalizes the traditional rectified linear unit with a slope for the negative values. So,
I've never heard of this one. Okay,
oh,
but
okay.
yeah,
Um, so ReLU is just basically this
right.
0 on the negative and then some positive value when you go here. PReLU is basically that and then this. So on the negative side, you have some slope. Does that make sense?
That does, yes.
Yes, as you can see, that's that. We won't go into the details of Prelude, but it might be important if we try and implement this from scratch. So the last thing then is you extract an image embedding from here. So you have your image, pass it through the backbone, do gem pooling, apply it to the neck, and this is where you have your image embedding, and then finally you have your head, which is doing 81K classification. All right, so this is the 81K. That means they're using the V2 version of the dataset. Hello?
Yep, I'm here.
Oh, sorry, I think I lost. It's just in my in my earphones I couldn't hear you. Okay, so
No
then they're
worries.
using arc margin for your thing. So this pipeline basically means that you still use the labels for your training set, but instead of like classifying to 200,000 because you're using a subset of the data set, as I mentioned before, is like you have this V2 version. You have your so right now they're just saying we're using this we're using this train version of the data set, and we're using 81K labels, and this is V2. So what you can do is pretty much follow this, and then you have a model that can take 512. So, oh, sorry, 1 second. I pressed the wrong button. Where did that go? Oh, I pressed Control W. My bad. So you have this, right? So let me put it there. So basically, you have this. You take these labels here, you pass them in here. This becomes your data set, and then what the model is now capable of doing is like you're able to extract these image embeddings. So you could do that for your test and train, which looks like test looks like this, train looks like this, and then you can like, oh sorry, these are the image embeddings. So they both look like this is my test, this is my train, and then what you could do is you could do the matching after. So arcface and gem pooling, while we don't know what they are, an understanding is that this can be used to extract more meaningful 512 image embeddings, so more meaningful representations of the image.
That makes sense.
All right. So they've basically done the same thing for 7 models. There's 2 SE ResNet, so squeeze and excitation. In case anybody doesn't know what squeeze and excitation is, I've written a blog that explains squeeze and excitation. So let's see where squeeze and excitation is. So I've explained what squeeze and excitation is, and there's like PyTorch implementation for it. This is basically the squeeze and excitation block. So they use like the SENet 101, which is this particular architecture, and they use B3, which is EfficientNet B3.
Mm-hmm.
So I've written about EfficientNet as well, actually. So EfficientNet. So if you want to know what EfficientNet B3 is, you can search the EfficientNet architecture. So this is basically the EfficientNet B0 baseline architecture, and then you do compound scaling after this. So there's compound scaling explained in this blog somewhere. There it is, and then that's your EfficientNets as well.
These are the
And then
V1
finally,
efficient nets, right, Aman?
sorry, yes, this is not V2. Yes,
Okay.
for V2 we did a paper reading group at Weights and Biases. So if you're interested in EfficientNet V1, that's the blog, and for EfficientNet V2 we did a paper reading group at Weights and Biases.
Aman's got you covered in any case.
Yeah, I would have done something somewhere, I guess. Thanks, Sanyam. And then you have your ResNet, and then you have Res2Net. Oh, there we go. I don't have Res2Net cover, but that's okay. It's just one. So let's do. What is this Res2Net? It's a new multi-scale backbone architecture. So what's the importance of this? I'm reading this for the first time. Representing
Same.
features at multiple scales is of great importance. That makes sense? Yes, it is. Recent advances in backbone CNNs continually demonstrate stronger multitask representation ability, leading to consistent performance. However, most existing methods represent multi-scale features in a layer-wise manner. In this paper, we propose novel building blocks for CNNs, namely REST2Net, by structuring hierarchical residual-like connections within a single residual block. Okay, so this is something, again, I'm going to bookmark and read for later, add to my reading list.
I've
So
added
this
it
is
to
again,
the list as well.
yeah, this is the process I actually follow in real life as well. If I encounter something new, I put it in my reading list, and before going to bed, I might just read through it. Um, so it's really helpful to, as you go, make notes of the things you don't know, because then you can go back and you don't have to like remember what you don't know. So that's why
This
I'm
is what you
asking
do
Sam.
before going to bed. Read
Yeah,
deep
I
learning
guess.
papers.
I mean, not every day, but during COVID, on weekdays, yes. So all right, so let's keep going forward. We normalize the images by the mean and standard of ImageNet dataset. All models use gem pooling, simple linear layer, and prelude, which we saw what it is. And then you have a 512 dimensional output of the neck as image embedding. Perfect. And then this is just what we saw. Okay, great. So how much of the car is actually left? Not much. So we're just going through that. So next thing is training strategy schedule. So as they say, there we go. We train all our models on GLD V2 only, because that's why you have the 81,000 labels instead of
Hmm.
200,000. Each model is trained for 10 epochs.
What's it?
Cosine annealing. Oh, it's like same. It's like 1.5 million images. So
Yeah, but
10
10
epochs
epochs
is,
is such a small number to think of, right?
yeah. I guess if you compare it to ImageNet, like this
Yeah.
size of the data set is very similar to ImageNet. And then you have papers like Vision Transformer or other papers that train for 200 epochs or 300 epochs. So yeah, 10, you're right. 10 is a small
Yeah.
number. Um, yeah, that's a good point. And then, but remember, it takes about 2.5 days on 4V100 to train
Hmm.
ImageNet. So if they're doing, but that's again for around 50 epochs. If they're doing 10 epochs, it's still a day of training on 4V100, I guess, just like rough estimates.
Were there any? I didn't catch that. Were there any limitations for this competition? I don't think so.
Not in the training. There's never a limitation on training. It's mostly
Yeah, for
about,
evaluation either, right? Because I'm
yeah,
guessing those would hit the limits for evaluation as well.
yeah, for evaluation you have like a 9 hour limit on your submission, as I
If you go
remember.
to code requirements, it should be there, I think.
Oh yes, thank you, Sanyam. So yeah, so your CPU
Hmm.
notebook less than equal to 9 hours, GPU notebook less than equal to 9 hours, TPU is not available.
Yeah,
All
I'd
right.
again be curious how did they manage to like. I'm guessing they might hit the limit with inference as well with all of these models. My intuition might be wrong though.
Yeah, I think your intuition's wrong because they won the competition, so they were able to fit the inference with these certain models.
No, my
But I
point
know
being,
what you
were there
mean.
any tricks with that? That's what I'm curious about.
Yeah, I know. I'm just pulling your leg.
Yeah.
So I guess that's the answer. Would that be in the pipeline? I think I've followed I followed the winning place solution from like Christoph Henkel and especially, so I think that's Christoph Henkel, right?
Yes, he's a retired construction worker who started
He's not.
Kaggle, and no,
I
that's
actually
that's the
believe
true
that.
story.
At some point, I actually believe that.
That's the truth. I don't know
It's
what you're
not,
talking.
guys. Don't fall for this. Nobody fall for this. It's not true.
You can ask Dieter. He'd say yes to that.
Yes, he'd say yes to that, but then look at one of the videos from this solution. He actually shows his face, and I think I saw one of the comments on YouTube videos that I actually thought you're older. So that was actually me as well. Embarrassingly, yes.
That video
Anyway,
got the highest click-through rate just because everyone was so surprised of his face.
yeah, I think I saw it first on Chai Time Data Science anyway. I think it was some. I think you were interviewing him for some different competition.
Yeah.
I can't remember. And then this team also had Philip Singer. I think he's, where is he from? Siam? I can't remember where Philip is from.
Philip is in Vienna, if I remember correctly, Austria.
Right. Okay. Yeah. So he's also another Cattle Grandmaster, and they both, I think, teamed up for this competition. Okay. So then, coming back, we took a nice digression, but we're coming back. They used SGD optimizer. They used a maximum learning rate of 5 ENEG2, which is quite high if you think of it. I'm used to seeing 1 ENEG2, but not really 5 ENEG2. But they might have a really big batch size, I think. That might make sense. That's only when you could get away with like a high learning rate is if you have a really high batch size. So of course that would make sense because they would be using like 4 or 8 GPUs. They'd be fitting about 30 images per GPU if they're using like 512, which means 128, and then that batch size, 5E-NEC2 might make sense. And then they're
Hmm.
using weight decay, which is for generalization. So that's just what's weight decay called? Like I forgot. There's like a term for regularization. Sorry,
Yep.
yeah, weight decay is a form of regularization. All right. Um, cool.
Again, I'm
So
so
then,
surprised by that fact that they're not. It's like nothing too fancy. Like you could do so many more things rather than just using SGD optimizer and just a simple learning rate. You could do many more things.
I think I can see why. Um, while I'm not trying to answer it for them,
Mm-hmm.
because you have 1.5 million images, and some landmarks only have 5 or 10. So if you do anything fancy, you're actually making it more difficult. Like if you add rotation, if you add more augmentation, if you add label smoothing, or oh sorry, not label smoothing, if you add mix up. I'm not sure why mix up is not a good strategy here, but maybe it's a thing we could try. But then even for mix up, how would arc margin work? So these are all questions that I have, and I don't have answers for them. um how would cutout work, how would cut mix work, or like questions like that. These are like standard techniques that you see. Gain leads to gains. And then um I think because you have that bigger data set size, and a long tail, which basically means like you have some images, we have some labels with only like 5 or 10 images. In that
Yeah.
case, an horizontal flip, or like just basic stuff would work as long as you do it right. Because remember, then you also want to use this backbone. Oh, but you could still do it. Okay, never mind. That's just a thought. All right, ranking post processing. So this, I guess, all of this, what this method has been explained here, all of this could be used to extract then 512 image embedding for each of the images, and then you could use cosine similarity uh, or similarity approach to just find a similar image in the train set, and then you could use that to make the predictions. So this could be a good baseline, but of course there's some post processing after. So let's read about post processing. As previous editions of this competition have shown, so a good thing here is that just like us, the greats like Philip Singer and Christoph Henkel were also reading previous year edition solutions when they first started with this, or probably they took ideas from previous year editions. So let's try and follow them. And then they found that properly ranking and re-ranking predictions is crucial to improve the global average precision metric at hand, that is sensitive to how landmarks and non-landmarks are ranked respectively. So one thing I didn't share or tell you, it's my fault, is like the data set also had non-landmark images. So just saying that thing actually makes the problem much harder. Like, we're used to classifying pets where every image has a pet photograph. But what if there were some images in there that didn't have a pet? And then your model not only needs to learn how to recognize pets, but it also
Hmm.
needs to learn how to know that there's nothing in this image. So it's just a whole extra long, it's just a whole extra amount of noise that you have to look after. And they found that properly ranking and re-ranking, which just means like, because for every output you have to provide a confidence score, so you can like rank and re-rank your outputs based on like the confidence scores. That leads to a good metric, or like exactly, because what you want is you want a good validation metric to win a competition. So they just found like good re-ranking or process, or like good post processing would help. So one major aspect is to specifically penalize non-landmarks that constitute a large portion of the test set. So they're penalizing the non-landmarks, which is good to see.
Hmm.
We tracked both overall gap as well as landmark only gap separately. Okay, thanks. That makes sense. And evaluated all ranking experiments on a validation set that resemble the test set quite well. So as I know of this fact, is that their validation set was actually a test set of the previous competitions. That's really smart. Um,
Hmm.
their validation set was a test set of the previous competition, which closely resembled the test set of this competition. So they had like a local CV,
That
which
makes sense.
is absolutely which correlates really well with the leaderboard. So now everything they did locally, and they could test like, okay, this approach works, this approach doesn't work. There are quite different ways to approach this ranking problem, and different ways can lead to success, but here is what we found to work extremely well. In the following graphic, which is this one, we visualize the main concepts of our ranking process. Test refers to the test set on the leaderboard. So this test is just is where you want to make the predictions.
Hmm.
So these are the images you need to rank. Train refers to the candidate images we can use to determine labels and confidence. So like, remember how I said you have 1,000 images you want to classify, you can find the similar images from 5 million images, or like that way. So you have train, which is where you find similarity between images. So test set is where you want to make the predictions, train is where you want to find similarity. And then one important thing we did is we increased the train set to include all available images from classes clean and full. That's a really neat trick. Oh wow, okay. Um so they trained the first model. Actually, let me try and explain this. As remember, as I said at the start of this, is like you have a V1, which is 5 million images,
Mm-hmm.
and then you have a V2, which is a subset of this, which is 1.5 million images. So they trained all models on 1.5 million images, and you classify on 81K. But then they trained their model on 1.5 million images and 81,000 labels. So now when you have extractor 512 embedding, this is the model that's used, that's trained on V2 clean. But once you have extracted your embeddings, when you're trying to compare it with your train set, what you could do is, like, instead of just having 1.5 million, you have 5 million on your train set. So you could use this model to now extract 5 million images. So your train actually becomes, or like the thing you have to choose from becomes 5 million by 512. Does that make sense?
It does, yes.
Cool. Are there any questions in the chat or anything I should be aware of till now?
No,
Okay, great.
no questions.
So, okay, good. So then the third place solution notes that extending the dataset to include also these images improves their training, which is, we agree, that's a good point. But what we found is that it is even more useful to be included in the inference process, because that makes sense that there are more images to choose from. This also worked well on CV, which is how we found it. And finally, non-landmark, which is this one, includes all non-landmark images from the V2 test set. So this is the V2 test set. Okay, that makes sense. But how would they know if it's V2? Non-landmark includes all non-landmark images. We then, this is their validation. So they used, this is what they're saying, because you had GLD Google Landmark V2 clean, and you had GLD V2. I have to confirm how they had labels for the non-landmark images of the GLD V2 test set. So that's something I'll have to confirm. So let's just assume you have non-landmark images, and you know that they're non-landmark images, and then you're trying to predict on test. Okay.
Doesn't
We
the
then,
clustering approach that we had just looked at, I'm calling it clustering approach, but really matrix learning, isn't that helpful for that?
yeah, but
Would
you
that
have the
provide
test.
labels?
You have the test set, but you don't know which ones are non-landmark. So I'm just curious on how that works. Is that just means, like, from the validation set you have non-landmark images? I just have to, yeah, I just have to think through how
Hmm.
this is think through how this is happening. So I don't know the answer yet. I'm just gonna skip over.
Hmm.
Okay, this is something same. Could you take a note of this as well, please? Just write GLT V2 test set, and we can cover that next time.
Done.
Thanks. So then what they do is you calculate pair similarity between all of these sets. So you're calculating pair similarity, right? So from the test set, you're calculating similarity with the train. So you have something like, oh, I have my test one image with, and imagine if I have 5 images in my train. So you have, like, test one is 0.3 similar to train one, it's 0.6 similar to train two, and so on. My test two is that much similar to, like, these images, and so on. And where are we? We then calculate all pair similarity between all these sets. So you calculate similarity between test and non-landmark, and you calculate similarity between test and train. A measures the similarity to all available landmarks and their confidence, of course. So you just have a similarity between test and train, so that becomes your confidence, like how confident we are. So as you can see, test and train two images are 0.6 confident, like models like 0.6, that's the value. I don't know how that's a confidence value, but it's a 0.6 value that the model thinks that test one is most similar to train two.
Hmm.
And then B measures similarity from all training to non-landmark images. So this is like test, and this is non-landmark. And C does not and C is the same for test images. That makes sense. Oh, sorry, B is train and non-landmark, and test C and non-landmark. Okay. The core idea is to now penalize A by B and C. Ah, I see. So to penalize images that are similar to the non-landmark images. A is calculated between each test image and the training image. B and C are calculated by the mean similarity,
Hmm.
and B and
I
C are
just recalled
calculated
we
by
had
the
also
mean.
discussed this, so I wasn't clear about this as well, and I did ask them during my interview as well. Now I'm able to recall.
Yeah, okay, so that's a really good point. So what they did, B and C are calculated by the mean similarity between the image and the top five. The mean similarity, I see. I see. The top five. So A is calculated between each train, and B and C are five. Okay, makes sense. All right, let me try and explain what's going on here. So test set is what you want to make predictions on. So let's say test set is 1K images.
Mm-hmm.
So let's say test set is 1K images. Train we know is 5 million images. Non-landmark, I'm not sure how many there are. So let's just say it's 100K non-landmark images. Okay. So what they're saying is they found similarity between 1K and 5 million images, right?
Yep.
So for each of the 1K, for each of the 1K, you get like this matrix, which is 1K by 5 million, so on. So for each of the 1K, you have like, oh, this is 0.1 similar to this, and this is 0.9 similar to this, or so on, 0.8. So for each 1K test image, you know now how similar it is to the train image. For B and C, which is this and this, they found for the test set, first they found the 5 most common non-landmark images that are the most similar to this. So you have, again, you have 1K by 100K, and then you find you, because it's going to be like, you're going to know how similar, like you're going to have values for this, right? That's the matrix that's going to look like. So let's say if I'm looking at test 1, you know that it's like zero point 0.2 similar to non-landmark 1, zero point 0.5 similar to non-landmark 100K, and so on. So just pick the most similar, like top 5 most similar, take the mean of it, which could be like 0.45, and then you do it for all of them. This could be like 0.5, this could be like 0.9, and so on. So now you know, like, out of my test images, the test 1 is 0.45 similar to a non-landmark, it is 0.9 similar to a non-landmark, and they did the same thing between train and non-landmark. So you have, in this case, you have 5 million by 100K. Does that make sense?
It does, yes.
Any questions on this?
Um, no, I don't see any.
Okay, great. So then for each image, now you have, so now you know like how many of the train images are similar to the non-landmark, you know how many of the test images are similar to non-landmark, and you also know like how similar test images are between. So this becomes A, this becomes C, this becomes B.
Hmm.
Interesting. So A is, in this example, A is 1K by 5 million, B is 1K by 100K, C is 5 million by 100K. Thank you. And then the whole procedure. So now you can basically, like, our baseline prediction could have been just based on this, right?
Yeah.
Can you see how, Sayam?
Yes. Yes.
For each image, you just basically pick the most similar image, and then that becomes your prediction.
Yeah.
But instead of doing that, if you have like a 0.75 confidence that test 1 is similar to this image label 10, and this test 1 is zero point 0.3 similar to a non-landmark, then what you could do is you reduce it by 0.3, so your actual similarity is now only 0.45. Does that make sense?
Hmm. Yes.
So that's what they're doing. That's how they're penalizing, or like, that's the penalty.
That makes sense. Got it.
Yeah, so oh, I've got to go. I'm just gonna wrap it up here. I'm just gonna read through this, and that's where I've got to wrap it up and go.
Sure.
Uh, but it's last 5 minutes, last 2 minutes, I guess. Then the first step is to penalize Aij, which is my test image, by Bj. Pick the top three most similar images, and then sum the confidence of the same label, and then pick the highest. Afterward, the score is further penalized by C. Okay, so pick the three most similar images and sum the confidence for the same label. Sum the confidence and then pick the highest. I need to understand what that means. So are you picking the three most similar images between A, so penalize A by B, pick the three most similar images and then sum the confidence for the same label and pick the highest? I'll have to read what this means. I don't understand by reading it the first time. So Sam, could you point this out? Just see how
Sure.
this, just write similarity matrix.
Sure. I was
Afterward, the
thinking of
score is,
KNNs, but that was just for the training. This is for post processing, so that this is not that. I think.
yeah, no, no.
Fine.
Afterward, the score is further penalized by CI. Using both B and C, it's a bit redundant, and just using either of those brings good improvements. With just using B is better than just using C. Makes sense. All right. This is where I'm going to stop. Actually, let's just read through the last one. Sorry, I'm not going to
Okay.
stop here. The whole procedure helps us boost the actual landmarks. Specifically, B helps us to eliminate noise from the train images, because of course, uh, like there could be train images that are non-landmark. So if you find the similarity of train and non-landmark, you can remove noise from the train. Like you can remove non-landmark images from train, right?
Hmm.
This gave both impressive boosts on CV and LP. Okay.
Are they
One more important
taking
thing.
mean of top 5 for matrix B as well?
Yeah,
I
for
think I
for
saw
B
something.
is top five. So it says here, B and C are calculated by the mean similarity in the image in top five. And then one more important thing to note is that when we're calculating cosine similarity, the similarity metric benefits from similarly scaled vectors. Okay, that's a good point. I didn't know that. So what we do is we fit a quantile transformer on the test set and apply them on train and non-landmark data sets. Okay, Sanyam, could you see what quantile transformer does, as in just take note?
Sure.
This makes the scores way more stable. Okay, cool. Um, so quantile transformer in my head is just something that makes the scales, or like the values of the vector, very similar between A, B, and C. So now you can like make things really easy using that. So it's like it benefits if they're of the same scale. So I guess let's stop here. Thanks everybody for joining. We will meet again. Um, no promises, Ben, but soon.
That sounds very dramatic. But hope you enjoy your Friday. Thanks for hanging out with us, and thanks, Aman, for leading this.
Thanks. Bye, everybody.